Yang berbahagia, Dato Engineer Dr. Haji Ahmad Zaidilaidin, Vice President, Academy of Sciences Malaysia, Professor Gerardus, Hooft, Nobel Laureate in Physics 1999, Mr. Uwe Morawitz, Chairman, International Peace Foundation, Yang berbahagia, Professor Ramli Bahrum, General Manager, Corporate Planning, Open University Malaysia, distinguished guests from institutions of higher learning, research institutes, government ministries and agencies, ladies and gentlemen. On behalf of the Academy of Sciences Malaysia, we bid you a very good afternoon and welcome to this dialogue on strategies to strengthen science education and collaboration towards achieving excellence in science, technology and innovation. This dialogue is organized as part of the Malaysian Bridges event series, facilitated by the International Peace Foundation and jointly organized by the Academy of Sciences Malaysia and the Open University Malaysia. Ladies and gentlemen, it is now a pleasure to call upon Yang berbahagia, Dato Engineer Haji Ahmad Zaidilaidin, Vice President, Academy of Sciences Malaysia, to deliver his welcoming remarks.
Assalamualaikum warahmatullahi wabarakatuh, and a very good afternoon. How are you feeling this afternoon? Are you all awake or are you half asleep? I must say that I was very fortunate this morning to be listening to our guest of honor, and he gave a very interesting lecture. Unfortunately, some of you probably would have missed it. But very, very fortunately, you have the chance to hear him again today, but not on the same topic. But I can assure you that he will answer your question very, very well. Ladies and gentlemen, I think the MC earlier had already mentioned a little bit about this program that we have, and I must say that I have to compliment the people involved in getting this dialogue together. This organization and the dialogues that we talk about towards the culture of peace, facilitated by the International Peace Foundation. So we have with us too Mr. Uwe Morawitz, who is the founding chairman of the International Peace Foundation. So he too will be involved, I hope, in the dialogue session afterwards. Ladies and gentlemen, the object of the dialogue is actually for you to listen to this gentleman, our Nobel laureate, rather than to listen to me. Therefore, I will be as short as possible. I do not wish to introduce him with his CV because you already have it in your hand. But what I propose to do this afternoon is for him perhaps to start talking about himself. And this is what I'd like to suggest, because the topic that we are looking at is strategies to strengthen science education and collaboration towards achieving excellence in science, technology, and innovation. My one simple question is, how does one become a Nobel laureate? What kind of inputs in education, commitment, conviction, hardships that one has to undergo before one can be chosen as one of the recipients of this, the most prestigious award in the world? So I will already start the question for you, and I hope that our guest of honor, Professor Gerardus will be able to answer this question. But subsequently, We would also be looking at the ways of strengthening science education and also collaboration that is possible between institutions, whether they're research institutions or institutions of higher learning, in order that we can achieve an excellence in science, in technology and innovation. So ladies and gentlemen, it gives me great pleasure in inviting Professor Gerardus at Hooft to address you. But first, maybe you like to be there or you like to be here. So it's up to you. Let's give him a warm.
Yes, I guess I should stand somewhere as a microphone. Thank you very much. It's a great pleasure for me to be here. And actually, this morning I already said a lot of things and tried to say a lot of things, which makes it difficult for me now to add much more. Regarding the first question you asked me, how do you become a Nobel laureate? And you also want me to say something about myself. That's difficult. I didn't really plan to say something of myself, except perhaps the following thing. When I asked you that question, when I was a student, or before that, just a high school kid, I was in an extremely fortunate position that an uncle of mine was a theoretical physicist, and I really admired him very much, and I wanted to be as smart as him, and also I had set as my aim to discover new things about nature. And I had to explain that when I was a very small kid, I wanted to become a space traveler. I wanted to invent a spaceship and then go into outer space. But the only existing spaceships, or the spaceships people were about to be constructing, were huge machines which produce enormous amount of fire and are very costly. I wanted to invent something very cheap to go into outer space. But I realized that if you want to invent that, you have to understand the laws of nature, the laws of physics. So I decided to become a physicist. And then I discovered that actually making something out of physics is very difficult. You first have to understand the theory. You have to be like Einstein, understand how nature works in theory. And this is how I became a theoretical physicist. I can actually go on like that. If you want to do theoretical physics, you first have to understand the laws of mathematics. And naturally, the next thing would be that I tell you that I became a mathematician. But no, I stayed a theoretical physicist. But I do like mathematics a lot as an instrument to understand nature, because nature is extremely mathematical. And if you understand the laws, how to do a mathematical calculation, how to set up a theory mathematically, how to formulate questions in mathematical terms, that is extremely important. Anyway, my uncle, whom I address very frequently to help me along to become a theoretical physicist, he would often visit my family. He was a very devoted physicist. He was always like a bachelor. Because he thought that being married was of no help to be a scientist. But anyway, I usually asked him questions, but very often his answer to my question was, "Why do you ask this question? I think you're asking the wrong question. Why do you want to know this?" And then I tried to explain that, well, I want to make this spaceship, I want to find anti-gravity, and so on. Then he said, well, let's stick to that. Why do you want that? Why do you want, what makes you think anti-gravity, and what makes you think this, and what makes you think that? And then usually he pushed me back on the right track, because I was completely in the forest already. So, and that I found extremely instructive, that he didn't really answer my questions, but he questions my questions first. And but then later on learns that no authority is sacred. And this is already what I said this morning. I said something about authority. As a scientist, you should question authorities. And That, I think, was something of an obstacle, particularly in this part of the world, where people have enormous respect, they venerate authority. And so, whether it's justified or not, if someone has authority to tell you how things are, you are not in a position to question. Well, we have learned already from the early age on, we are always in a position to ask questions. No matter how much more respect and standing someone has in society, if that someone tells you to do this and do that and that, you will say, okay, I can do that, and so, but why? And what is the reason why I should do things this way or that way? And you are always entitled to ask some questions, to question whether the findings that you find in the textbooks are actually correct or not. The textbook is not sacred, there may be errors in your textbook, there may be mistakes made by your teachers, and you always need that independent attitude as a scientist. And that, of course, means being very critical, but then never forget to be critical towards yourself. If you believe you've understood something, or you believe you've discovered something new, or you believe you've made a highly important discovery or invention, always ask questions. You know, someone comes along from outer space, God knows what, and says you've got it all wrong. You must always realize what could that person possibly say? Why am I totally wrong? And then you say, yes, actually, that person put a point. This and this and that, which I've said, is not based on very sound understanding. There may be something wrong with it. And your attitude should be such that you should be yourself the very first person to criticize your results or your understanding. And then if you totally fail to criticize yourself, you'll have to await and listen to the criticisms made by others. So being critical, including being critical to yourself, is very, very important. This, I discussed this morning briefly, you can't quote people who do pseudoscience. They are often distinguishable from other scientists from the fact that they're not sufficiently critical. They believe their own results beyond and against all the odds that actually are. So this is the attitude you must have. Now, these are important ingredients, but not all. Let me give you a little story. When I was a kid, all my schoolmates wanted to play soccer, so they wanted to play football, and on every little schoolyard, no matter how big or small, you always saw a few heaps of clothes here, heaps of clothes there, and that was the goal on one side, and that was the goal on the other side, and there was sand, the terrain was not rectangular at all, but anyway, there are two pieces of things, and then something that looked like a ball was being, and these little kids were running around behind this ball very fanatically and trying to score on the other side, and I was the only one who didn't want to play, and just because I had other things in my mind. But then Holland was very high on the list of football nations. The country made, was winning tournaments and soccer games and so on. And I realized, of course, that was because the kids, from a very young age on, play soccer on the streets. And later, of course, I didn't see so many people playing soccer anymore. The kids are now busy with their iPods, their computers, and whatever, and they don't play soccer so much. So I am not surprised that Holland lost some years later football matches because the kids are no longer interested. But then I went to Brazil and I saw again on every little beach the kids were playing soccer. So I was certain that Brazil was going to win the next national team. And they got very high. I'm not sure they actually won, but anyway, it's quite clear from this experience that if you start from a very young age to play in a very simple, one-minded way, the thing you really want to do when you grow up, then this way you generate champions. And so expertise starts at a young age, you generate champions at a young age, but of course you never know who of those kids will become a champion. Then I found there's a few lessons on this that one can learn. One is that sometimes I see that people who prepare and organize the educational system in my country or in other countries, I often think they're making certain mistakes. And one of the mistakes in attitude I find in people who devise educational systems is that they want to make it as simple as possible. It should not be difficult, because then they won't be able to follow and understand it. And also they say it has to be geared on their daily life experiences, then they will understand it. I think there are two errors made here. One is the error of trying to make things as easy as possible. That is not necessary at all. Kids are very, very smart. Their brains are growing. They can absorb all information very, very well. It has to be presented in the right way. If it is difficult, they can cope with it. And to prove that is very easy, because you see often little kids playing with scooters, and actually the scooter has, by law, engines which makes them not run faster than very slowly and equally, so that they can stop whenever a pedestrian comes in their way. Now kids want to go fast on their scooters. So what they do is they find the tools and they take the whole thing apart and put that together again and remove all the restraints put there by law, and then they can, in a very noisy and fast way, go much too fast and much too noisy on their scooters. This, I think, is very difficult, but they manage to do it. Same thing with music. Music is very nice, and kids like to do it, but it's also hard. So to play guitar or piano or any other instruments, and to excel in that field is very difficult. Same with many other sports. If you see how devoted kids can be to excel in a certain domain, you see that being difficult is not a problem. Difficult things can be coped with, provided you find sufficient motivation to do it. Then nothing is too difficult, also for children. And so the teachers then want to adapt the teaching material such that it is geared onto the things they exactly understand and know already, their daily life experiences. Well, the problem with that is that the science of daily life experiences is actually very difficult. And if you want to make things easy, you should start at the beginning, but that's not your daily life experiences. If you want to have the dynamic ride of a soccer ball which goes in the air, or a tennis ball, you have to realize that while you go in the air, there's air friction. There's not only Newton's laws, there's air friction. There's the effect of the spin of the ball. Usually these balls have attached, so they don't go in a straight line, they go around the corner. And all that makes it extremely difficult. So trying to teach science, basic science, by making an appeal on the daily life experiences is not always, or very often not, the best way to teach science. You have to do the science of electromagnetic fields, the science of elementary particles, of spaceships or planets in the universe, because they happen to follow much easier laws than the soccer ball or the tennis ball that you're playing with. So you should learn science where it's easy, but that's often not the daily life experiences. And another error that I saw people make is, and this is a very serious problem in my country, that people think it's a bad thing to teach kids to use tables and arithmetic rules. So they suffer themselves, and they see a little kid learn the tables from 1 to 10, multiplication tables, or to learn geography or history by making long lists of numbers or long lists of towns and countries with their capitals and so on. Truth of the matter is that learning tables and rules of arithmetic is easy. Kids have brains which can store enormous amounts of information. And tables they require no deep understanding. They can learn them from very early age on. Whereas the educationists are come to discover that very often when you do a multiplication of two large numbers, you're too lazy to do the calculation explicitly, digit by digit. It's much easier to first make an estimate of the answer, and very often that estimate is good enough. So they said, we're not going to teach our kids to learn all these multiplications digit by digit, and the tables, literally, they don't have to learn them by heart, because you can do that on the machine, but we teach them how to estimate the product of two numbers. The mistake you make then is that you try to teach these kids tricks to estimate the product of two numbers. Those tricks are much harder to understand than the arithmetic, the tables that you learn by heart, or the arithmetic, which is the rules of how to multiply two numbers, hard but admittedly slow way, and the dull way. But actually, that's the easiest way in the sense that it doesn't demand any higher knowledge. Whereas these tricks that they want to teach the kids do require all sorts of higher experiences. Higher experience the kid doesn't have. So then teaching tricks is going to be a big failure. And I saw today we complain that the education system becomes no longer as good as it used to be because they use methods that actually fail in practice. Well, I think I can continue this way with what I think are good rules and bad rules. The thing I forgot to say is I would ask the question, how do you become a Nobel laureate? Well, here I can say this is the wrong question. Because you should say, I mentioned also this morning that the total contribution made to pure science by Nobel laureates is negligible compared to what all the others made. In fact, when you become a scientist, it's nearly certain that you will make a discovery in your field. The discovery will not be a earth-shattering discovery. It will probably be a small thing. I mean, biologists will like to learn why are the wings of this butterfly yellow and that butterfly brown, or why does this butterfly grow bigger than that butterfly, or something like that. And you discover something that nobody else knew about butterflies, or you discover something nobody else knew about pollen, or a particular kind of toad in a country that nobody ever searched for toads before. But yes, there is a toad there, and the animal has unusual features. You will be the very first scientist to discover such a thing. Same thing about elementary particles or atomic physics, nuclear physics, any other field of science. A scientist who decides that this is going to be his or her specialty will discover something. Not something for which you get a Nobel Prize, but something that gives you pleasure. And that's very important, that when you become scientist, you'll have the pleasure of discovering things that nobody else knew before. And that should be your great motivation to do science, to have the pleasure of discovering something. That's how you get started. Well, once you have learned how to discover things, small things, there is a possibility beyond your own control, but there is a possibility that you discover something big. And if you discover something big, and you are to be the lucky person at the right time, at the right place to discover something big, you've learned how to discover small things, then you can discover big things. And that may happen to you, but that is just a chance process, and then you'll be standing here being a Nobel laureate. So that might happen or it might not happen, but that should not be your motivation. Your motivation should be that you should enjoy being a scientist, enjoy these small discoveries which you will surely make when you are there. Anybody who decides to go to science in this room or elsewhere will make these small discoveries which give you pleasure, which help you understand that this is why I wanted to become a scientist in the first place. So that's my introductory remarks. Any sort of discussion, and I guess that you will be telling me in what direction the discussion is to go.
Thank you very much, Professor. Would you like to sit down or would you prefer to stand?
I don't mind. I can sit down here.
Yes, it's more comfortable. Yeah. Right, so this is the time for dialogue session. It's one way to keep awake. So please ask as many questions as you can. I feel that you really benefit from asking the questions. It doesn't matter if, like me, I ask the wrong question. My skin is too thick already.
I'm sorry.
I'm quite used to this. So please, yeah. But please just make your question brief and to the point. Your name first.
My name is Lal from Good Morning. If I may just start off, Prof. You see, Malaysia is a long way, to my mind, from getting to the position of Nobel laureate. What kind of suggestions would you have to, although we've earned some awards in inventions and so on at exhibitions and things, what would you say are the key essentials to this drive towards excellence, towards trying to get a Malaysian Nobel laureate in the near future? Thank you.
Chairman, I think you sounded offended by my remarks, but I want to emphasize that sometimes scientists sound rude and being critical, but that is the right attitude that scientists ought to have. So anybody, well, if you say something, I say no, it's something else. But some people feel offended or they are afraid of saying no. But that's the way how to try to get closer to the truth. And you're certainly entitled to criticize everything I say and say, no, you've got it wrong, and you try to get to the truth. So you can say, okay, well, one question is, well, how could Malaysia come closer to the Nobel Prize? I say, first of all, it's a chance event. You don't have there Jeeper, who was also giving talks of this sort. He said that his real experience was that you have to be extremely lucky to get the Nobel Prize, and you can't force luck to yourself. But you can try to be at the right place at the right moment by doing science. So Malaysia will get a much bigger chance of getting the Nobel Prize if it has a large number of scientists or people devoted to science who, as I said before, are making small discoveries all the time. And by making small discoveries, you are in the right position, in the right frame to make a quick discovery from time to time. And science is a bit of small questions and big questions. And my attitude has always been in the past, I want to answer the very, very big questions of science. I will not always succeed doing that, of course. Mostly I will never succeed doing that. But the big questions are surrounded by very, very many little questions. And so first you have to identify what the big questions are, what the little questions, the small questions are. And you very often realize I can't answer the big question, not directly. But I know there are very, very many smaller, less glorious subjects which you can study, which ultimately are related to the big questions. So answering these small questions will help. So you have to learn how to answer the small questions. And as a scientist, yes, you will succeed answering some of those. Like why does one butterfly have brown wings, why does the other have yellow wings? And by answering that question, maybe that's not so important for science, but eventually you'll discover what makes it that certain species have certain different properties, and you might end up answering a bigger question, how does differentiation come about in nature, and or something of that sort. I gave a rather simple example here, but there are many such examples in science that are actually very big questions, but the only way to get there is by first attacking the smaller ones. And that's how you train the scientist, by having him answer the little problems that are facing us. And science is completely littered with tiny questions, questions which are interesting, perhaps only for the person who goes through the mud to try to answer those little questions. They're often difficult to answer, but at least doable for an ordinary person. And then, once you've generated a whole breed of scientists who are able to do that, there'll be one or two among them who stumble upon a bigger question, and now with all the experience they have, they are in the right position to try to answer the big question. And then the question might be considered in Stockholm as being something worthwhile or nice. And this is, of course, as you might well imagine, a chance process. It may happen, it may not happen, you never know. And then you must have the attention and interest by the people in Stockholm. Again, the people in Stockholm are an authority, and scientists often question their decisions, if they choose to make the right choice or not. They are doing their very best, and I know that, I've seen what they're doing, and we've seen the last years that they made a choice of Nobel laureates, and often the experts at the end say, yes, this was a very interesting and important choice. So yes, they have lots of authorities, but sometimes my colleagues think they were mistaken, they should have done this or should have done that. But this is always the case. So this is as close I can come to not answering that question.
Hello, I do have a question. My name is Razak and I'm from Hooft. For the past 6 years, we in Malaysia have been learning science and English, and that is one way that the government think of to strengthen science education. So I'm not sure whether what is your first language. I think it must be Dutch, right? And so do you use Dutch to teach science and mathematics, or do you use English?
Okay.
So maybe you would like to tell your experience in your country. If you are teaching math, science, and mathematics in Dutch, you can do so well, right? Or and we'll try to relate to our experience as teaching science and mathematics in English.
Well, that's an interesting question, the question of science, because I don't know exactly how it's done in this country, but our native language is usually not English. In Holland it is Dutch. It's a language related to English. It is so linguistically it's not very far away, but it's definitely a different language, close to German. We teach our primary and secondary schools in our native language, of course, not in English. Although nowadays, even some people say you should even start with English in kindergarten, but we still don't do that. But already at primary school, kids are certainly they are confronted with the English language, and they pick it up basically already on the streets. So already little kids know a few English words, and they learn English very quickly because it's such an important language today. So we teach our science. The undergraduate lectures are still in Dutch. So we have Dutch textbooks and or lecture notes, and everything traditionally taught in Dutch. But then after their first exam, they do their graduate courses, students do their graduate courses, and those are nearly always in English. And that has been a shift recently, that when I was studying, most of those are also in Dutch. But now we choose English for two reasons. One is that the text is already in English anyway in the textbooks. And the second reason is we want to globalize, so we want people from abroad to be able to follow our lectures, and we want our students to have no difficulty in going to other countries and learning or continuing the study there. It's a good thing to adapt the language. So we switch to English between undergraduate and graduate courses. That choice could be another choice. I think in different countries, different rules would be valid. So So here I would think probably you should make the decision already earlier than to decide to teach English. And that will be a stumbling block for many kids who do not understand English very well. So it's a very good motivation to learn English. It's now the language of science. I'm a bit sad about that. I wish the language of science would be Dutch. For some crazy reason, people chose the English language as a language of science. So now, yes, well, that's the way it is. And diplomacy also goes for, in many respects in English, but sometimes also French or German. Still use other languages for diplomacy, unfortunately. But I think eventually they also choose English. English is a very powerful language. It's a crazy language. English itself is speaks of other languages, you know. So, and also the relation between spelling and pronunciation is awkward in English. In Dutch it's much more direct. It's a much more pure language. But, well, it's the way, this is a decision made in history that we can't change anymore.
My name is Ahmad. I work at the Malaysia University of Science and Technology. I'm also a fellow of the Academy of Science. I think we're all familiar with the problems faced by the world now. We are up against things like climate change, problems of energy becoming short in the future, and there's concern about, recently there was big hoo-ha about the increasing price of commodities and fuel, but of course lately this has come down. And so many problems facing the world, and over the years, actually science has made tremendous contribution to solve some of these problems. And in Malaysia, like in many countries, we are trying to capitalize on science and technology to actually develop our resources for wealth creation, for societal well-being. But I was actually quite interested in the things you said this morning, that if we really use science and technology, we may not have this problem of poverty, and we can still increase our population without worrying about our energy consumption and the like. But there are some other thoughts who are concerned about this. They're saying that if we really maintain our current lifestyle in terms of energy usage, we may not last very long in terms of the energy that is available to us. And one way they say is to cut down the population if we are to actually survive and be sustainable. Now, I think everybody agrees that science and technology has a role to play in all this. And science and technology, I'm told, flourishes in a culture which promotes disagreement, which promotes a lot of curiosity. But in Malaysia, it is said that the culture here does not promote disagreement. There is a lot of clamping on expression. And as you rightly say, our culture is also one which does not question authority. And this is not conducive for science and technology, and not to mention innovation. So how do you think, as a person coming from a science background which actually finally culminates in this very noble prize, how do you think Malaysia should pursue a course of action in terms of policy or whatever to actually change this kind of culture? It may be over a longer term period, but how to actually move from a culture of suppression of dissent to one which promotes and encourages disagreement. Thank you.
Thank you. These are a lot of questions actually. There's a problem of climate and energy and the fuel price and so on. As I stated this morning, I do believe that science alone, if it were for science alone to solve these problems, it would be doable, but the problems are being made more complicated by questions of economy, by questions of political power, by also questions of religion, which are sometimes standing in the way. And all these together make it a lot harder to address these problems. When a country suffers from a lot of poverty, it's very hard to change anything. Your first priorities are no longer to address the real problems of energy consumption and so on, but to address the problems of poverty. And then often the military option is being sought, which has usually completely contrary effects different from what we aimed at. When I said that I think science can solve the problem of the energy crisis, of even climate change and all that, it is because I think that energy consumption can go down per person very easily without really changing our lifestyle very much. We should change our priorities perhaps, but I'm sure that many of the things we do can actually be done with using less energy. Our machines could become more efficient. Our automobiles would consume less energy than they do, and we would try to burn the fuels in a more efficient way. We could try to search more for renewable energy forms, alternative energy forms. The discussion is a very hefty one in Western Europe, like everywhere in the world. How should we do this? My belief is we should address all possibilities to answer questions. So science is flourishing when you investigate all possible answers. So I'm very strongly in favor of trying all possibilities to solve the energy problems. Like all, say, solar energy, wind energy, water energy, energy of fossil fuels, and nuclear energy. You should investigate all these options together, and I'm sure that a sound mix of all these different solutions together will help humanity for many more centuries to live in a comfortable way. Even while the population might increase. At the same time, science should investigate the problem of population increase. The population cannot increase indefinitely. There is a certain limit that this planet can handle. So the population, for instance, cannot increase exponentially, because that's much too fast, whereas the resources of this planet will not grow exponentially. They will grow. We'll find better ways to grow crops, we'll find better ways to produce energy, we'll find more economic ways to spend energy, or economic ways to redistribute food over the entire planet, so that food consumption is often food is often consumed more than necessary. There's a big problem in the Western world of obesity. People simply eat too much. People throw away too much food. These things could be addressed also scientifically. How can we, technologically, how can we distribute food in a more even way, in a more healthy way, so that actually less food has to be produced than we normally do, rather than more, without decreasing the comfort of our lifestyle, because we are going to be a very spoiled race. We want to have all luxury we can think of. But luxury doesn't mean that we have to throw away food. But it has to be a natural way to produce exactly the amount of food you need. I think that there are many ways here for science to improve the situation. As for, I think you mentioned in Malaysia that there are disagreements, but usually there are authorities that are not allowed to question. I think we should make a clear distinction between being critical and accepting or not accepting authority on one hand, while having respect for the other on the other. You should respect the authority and say, in listening to what they want to tell you, and you say, well, if at all possible, we're going to be obedient. But if there really is a problem, and if you really think that we are pretty sure that this is not the right way, then we should be critical. And that doesn't mean we should start a fight or shoot someone or terrorize a population far from it. But we should go into disputes, we should argue, and we should question, and this way try together to reach a better truth than a single person can. And that's again something that we see in science very much. No single person can understand much of the truth that we arrive at in science. Science is a collective enterprise. All of humanity is much, much smarter than any single person in here. So Mr. Albert Einstein was very smart, but not at all as smart as the whole combination of all humans together. So many, many discoveries, even in Einstein's time, were done by other people. So the entire human community is much, much smarter than any single person. And we should be aware of that. It also means that no matter who the person is, what kind of authority he or she has, we should have much respect for someone who has achieved a lot, but we should never stop being critical.
Yes, thank you very much. I have an agenda today because there's the other side of the strategies of the topic that we are discussing, and that is the collaboration towards achieving excellence in science, technology, and innovation. I would like, if we can, next consider questions on collaboration. Because in this room, Professor, we have a very interesting mix of people, and I talked through to them just now. There are those who are from research institutions, there are those who are from universities, there's a teaching university that came, there's also Australian University, Monash people. And so we have a very interesting mixed bag of people here. My question is really, how do we collaborate effectively towards achieving excellence? So those of you who would like to question to this, I would like to ask questions along this line on collaboration.
Mukherjee from OUM, Open University of Malaysia. In your introduction, actually, you didn't let us know very much about your postgraduate days and how did you develop your research, how did you build up your team, and how many people were in your team, and then did you collaborate between your institution and other institutions in Europe and in US. So these are the things which probably give us some inkling about how the collaboration could build up a future for scientific research.
Okay, it is obvious that nobody can work by himself, by herself. You need other people constantly around you, partly to criticize you and to confront you with other opinions and with other approaches to the topic, and also to document things you know, but there are other technologies, there are other people who have other ideas, and there are adjacent fields in science of which you also want to know what they do. So it's very important always to have groups of people. It does not mean that you have to collaborate literally all the way. And I myself am a very bad example in this respect, because I did most of my work alone. But alone with the quotation marks, that is, the deep thinking and the ideas were perhaps for myself. But I would not have been able to function without having an environment around me of smart people who come with smart ideas all the time and whom you want to talk to about your results and who ask you questions like, I don't think you've done this right, or how do you know that, and you can't do it some other way, and so on and so forth. So in that way, you always need a scientific environment. And for that reason, you want people to gather together very often. And in my case, it's at different stages. We had a good functioning Institute for Theoretical Physics, which has a staff of different professors and students who talk to each other a lot and discuss their results. Then at the national level, there were 4 or 5 universities very active in my field. So we would have monthly gatherings together with the other universities and yearly for all the topics in physics of the country. There would be joint conferences. Then at a later stage, the Netherlands is too small as a country to do science alone, but in my field of science there were other neighboring countries where the same topic was being studied, in particular in France, Denmark, Germany, Italy, Greece, and England, and some other northern countries. So we would often have joint meetings. When the first joint meeting was organized, and I was still, I just started with my graduation work, and I had done the first discoveries in gauge theories. Those just three universities. That was Utrecht, where I had been working, with Paris and Rome. So Utrecht, Paris, and Rome. The universities Utrecht, École in Paris, and what's called the University Sapienza in Rome. We came together and had a joint meeting. And we called that a triangle meeting, because obviously three universities, so they formed a triangle. So these are called triangle meetings. But very soon the triangle obtained more angles. So there was University of Leuven in Belgium, there was Copenhagen, there was University of Crete in Greece, and every now and then from other places people come from elsewhere. So very soon the triangle had 6 angles, and but we still continue calling it a triangle every year. This is very successful because people were having very similar problems which we could study, and so we studied those together. Now that was in my field of physics, but there are many other fields of physics where similar approaches were used. We came together and studied and joined forces, joint seminars or joint workshops, and so they are in all fields, often in different places. And I mentioned the Institute for Summer Schools, and in Europe we have various summer schools where in one university some people organize the summer school. They invite lecturers from all over the planet, but graduates from not too far away, but sometimes not too far away, and who are experts in certain fields, and the graduate students from all over the world are invited, but often the graduate students from those universities. So the summer school in France, in Les Houches, is a famous example in our field, but there's also RHA, there's also Pages, and there's also other schools. But there are many other places where people hold, typically in summertime, they would have these schools. So it's often important to unite, and in my case actually all theoretical physics is united. Again, not obvious, because in some other universities it's arranged differently. They have different subjects to study, like solid-state physics, nuclear physics, low temperature physics, particle physics, string theory, And all these groups would have their separate theory departments. And every now and then theories would come together, but they would have separate department theory. And we said, no, we want one department where all of theoretical physics is done. So we would have much more intense communication with people who do theoretical physics, but in other fields of physics. So that's another way to collaborate. But it is obvious that you can't stand by yourself. You need an environment of people who, particularly people asking nasty questions, and questioning whether your results are correct.
Prof magazine, as you know from this morning, but this is a personal question. Because you see, collaboration, I think what Bridges are trying to do is getting the East and the West to work together. But the scientists in the East, I think all of the people in here, they do believe in some kind of religion and believe in God. And they think, okay, for me, as a Muslim, I think religion actually can enhance science. And for the West, it's not like that. And it's a question of two egos. Okay, the religious people think they are right, and the scientists think they are right. And how do we break those barriers? That's my question.
Well, that I think is a hard question. So I didn't really hide the fact that I'm not a very religious person. So I adopt I embrace the scientific answers without really bothering too much about what the religion has to say about these things. But I also said in the beginning of the lecture, people are different, and science thrives because of differences. If everybody would have the same approach, we would be nowhere in science. Fortunately, there's so many different people with different approaches, and I found Abdus Salam is a good example. He's from, as I said, well, he was from India, and then turned out that actually Pakistan. He is from, so he's a Pakistan physicist, and he was also a very religious person, and so he believed in his religious ideas as well, and he believed to be inspired by religion. Now, how and where you get your inspiration to research some things is a very personal thing, and I would be the last person to say that you are not allowed to get your inspiration from religion. Maybe you do. Be you have an idea about creation and an idea about the secret truth. You might think that they are hidden in religion. Well, the fact is that often people with such conviction, they do discover some things. That you are so much convinced that you want to search in a certain direction, that you might find something there. But someone who's convinced in a certain other direction will also find something. So there's nothing wrong with being guided by religious ideas. Maybe I'll say it later.
From University of Malaysia. I have a question that today the results of all the investigation that has been done before, suppose we know all of them, collect all the information from books. For future, is it necessary in physics to have a new interpretation of the previous understandings, or do we need to do more experiments to improve the science and technology? This is my first question. Second question, because I'm a teacher, I'm teaching physics for a long time. To make understandable problems of physics in my class, I try to explain it with a real question. With a real question, real problem. For example, in the class, I want to teach mechanics. I send a pen up and it moves very complicated movement, and to interpret this it is very difficult, almost impossible. So under these certain assumptions, explaining how we can find out or write mathematically the way that can interpret this movement, for example, under this assumption, to make it understandable from different point of view or limitations. Is any advice that makes it possible to teach physics faster, understandable for students? Experiments give them observation to the student, but explaining them theoretically a real life problem is too difficult. Only under certain assumptions we can solve it. Then the questions appear when I want to solve this real problem. A lot of questions one after one. And then the enjoyment is not only through knowledge and learning, but also enjoyment comes to me when I know that I don't know. A lot of other questions come to me. And at the end, I understand that I cannot solve any problem unless I have some assumptions. I want to know your opinion. Thank you.
Well, Gerard, you mentioned experiences in class, how to teach some things, and you discovered the thing which I also said, which is that if I throw a pen in the air, I want to know how it moves. It's very complicated, and to start teaching that to young kids is perhaps hopeless. So, however, kids are not stupid at all. So they do understand when you say this is a difficult problem, because look how complicated the thing behaves. Let's try to make it simpler. And you may discover that actually the planets along the sky move along simple orbits, which you might be able to understand, and then you might be able to calculate what these orbits are. So you can tell a kid that problems that they encounter in daily life, that biologically they can understand how a football goes because of so much experience. But actually, if you want to understand from basic science why a football or a pen moves in a particular way, then you have to analyze the problem, and that takes a lot of effort. Whereas there are systems in nature where the laws which are responsible are much easier to understand. So let's focus on those. And I don't think any people have difficulty with that. And they say, well, in the very end, to understand exactly how things work in life is complicated, but it's quite doable. If later in life you become an engineer and you want to know how a car engine works, you have to investigate everything. Because a car engine is a complicated device, but it consists of components, each of which you can understand. I have to put it all together. Fortunately, this is a science that has a long history, and people have solved practically all problems. And your assignment will not be to reinvent the car engine, but to investigate a very tiny detail in it and say this might be improved, or you might find some alternative in some very tiny corner of the car engine. And then you can say, now to do that you can use basic science, and you can you need to understand the laws of thermodynamics, solid state physics, material sciences, and so on. And this is doable. And there are rules here, but the rules can be illustrated not by the things from the daily life, because they're complicated, but by idealized systems. So instead of a pen, you take a point. Well, this is what's the point? The point is something that has no size to speak of, and so all aspects of its final size are immaterial. It's just a point that moves along a certain direction. And then the rules become simpler. And they say, oh, let's concentrate on the simple things first. That should be done in a systematic way. And I think if you teach science in a systematic way, it's much easier to get it. That's, of course, what you should do anyway as a teacher. You decompose a different problem into its simple parts. So the simple parts can be understood. How to put it together, that's mathematics. And to do that, you need a certain amount of training, which doesn't come by itself. It requires a lot of exercise. And you may or may not decide to go into this exercise and try to figure out how to do that correctly. So I'm not sure I'm answering all the questions, maybe not.
So the second question was about is it necessary the improvement of physics will be based on a new interpretation of or previous theories or previous understanding of concepts or models, or it can be happen based on more experiments. We need to do more experiments.
It is not an or, it is an and. So we have to do both. Today, the science of fundamental particles is so complex that we find it very difficult to make any improvement. We have what we call the standard model. It works perfectly, but it also contains a number of important question marks where we don't understand why things are the way they are. So, but these questions turn out to be so-called big questions, which are very, very difficult to answer. So there are mysteries there, and the only way to address these mysteries is to do the very best we can. So we have hundreds of scientists, each of which is standing on his or her toes to try to improve our present understanding, which means we have to do experiments, but we also have to think very deeply about our theories. And the theories usually are not overthrown by other theories, but they are improved upon in details. And we discover that maybe a rephrasing of the theory will improve it. And we might understand how to make small changes in the theory so that it fits the observations better, or so that it agrees better with logic, because the theory has several requirements. One is it should, of course, reproduce experimental results, but it should also be internally logical. There should not be an internal conflict in the theory, and very often there are. Like I say, one of the difficulties we had in particle physics in the old days when I was a graduate student was that existing theories were in conflict with themselves. They did not agree with themselves. And that was quite clear situation that people lasted very long. You can make a theory that at least is in agreement with itself, let alone in agreement with other experiments. You need, of course, all of that. You need a theory which is in agreement with itself, it doesn't have internal logical conflicts, but should also agree with observation. So you can't do one and not do the other. You'll have a wrong theory. It's wrong here, or it's wrong there, or it's wrong there. The correct theory is right in all these places. So it should agree with experiments. You have to do those experiments. And if you don't do the experiments, odds are that you'll have it wrong. And that is a lesson that history has taught us. If you don't do experiments, you'll not get the right theory. And the difficulty today is experiments in particle physics are becoming harder and harder to do. We've come very close to the limit of what we can do. Well, we can still do a lot, but it's going to be very costly. And the big question is whether humanity will be prepared to pay the cost of another world machine. It's a machine where the entire globe will participate. That should include Malaysia, by the way. And so the entire world will contribute to make the biggest machine imaginable. And that big machine will disclose other features of elementary particles. And that experiment must be done. If we do not do the experiment, there will be certain things that we will not be able to find out. But of course the theory should also be internally logical. And that is something we can find out because we just need our minds and very, very strong computers to figure out whether there's any internal inconsistency in the theory. And that is an important strategy that we are all involved.
My name is Dr. Harudin. I'm from University of Malaysia, Faculty of Education. My question is this: just now you said that we should teach our students to ask little questions, small questions, instead of big questions. But I think one of the reasons why maybe science is not as popular among the public is because we don't try to address the big questions set by non-science approach like the religion, right? Religion, or should we start getting science to start answering this question? Should we try to explain life, consciousness, using the basic theories of physics, perhaps? So this is my question.
Well, it's interesting to hear from you what you consider the big questions are, because what is life is an interesting question, but it might not be the biggest question in science. In my field, there are very many different big questions. There are also small questions like this, why does this fly have bigger wings than that fly? Those you consider small questions. You just said that somehow physicists here or scientists don't want to discuss the big questions. I think under all circumstances, they should always have these big questions in their minds. You can't do without big questions. You can only properly formulate the small questions if you understand what the big questions are, and you must discuss those in your private meetings with a small number of people when you're discussing what you're doing. You have recognized, well, the big question is this one. We can't answer it because it's too complicated, and if we could have answered it, it would have been answered long ago by someone else already. But the fact that this is a big question is unanswered today shows that it's a very difficult one. But what we should do is rephrase the question and find out how we can peel off little bits, which are small questions, which possibly can be answered by doing experiments or thought experiments or logical analysis or something. And the only thing you have to do is try to think of something nobody else thought of before. Well, the big question has been thought of very deeply by very many people, but those little questions like the fly or an elephant, or a galaxy, why is this galaxy round, why is that one this strange shape, ask questions like that, which are also very big questions that people have addressed. But then, because our galaxies and stars and galaxies and so on, why are they this shape and not that shape? So, if you cut big questions into little ones that way, you'll find interesting questions to address, and eventually you'll make progress by first addressing those little questions. Well, it would be wrong to lose the big questions out of your mind. You should never do that. And that way, you are leading an interesting life as a scientist. You know, you tell your friend, look, those are the big questions that are dominating our field. Everyone wants to be able to answer them, but they're so difficult. And I'm studying this and this and this and that, and I can explain to you within half an hour what I'm actually doing that I'm trying to study, and I need another 2 hours to explain what I'm doing to try to answer those questions. And by that time you fall asleep because it's so uninteresting. It sounds so uninteresting to you, but it's interesting to me because I think it's related to the big question such and such and such a way. And again you come with a very long argument why it's related to the big question. Fine. This is the way we function as scientists, and we discover that an ultimate pleasure, even answering the small questions.
My name is Azan Abdullah. I'm from Senior Rexam. It's a regional center for education in science and maths. You mentioned quite a number of times just now that kids are not stupid. You know, if you really believe that, so if students study science, especially physics and additional maths, which is so difficult, and they don't achieve, then their achievement level is very low, do you put the blame on the teachers? Or, you know, there are just some students or some people who just cannot do hard science. Or even how much the teacher does, they still cannot understand. What's your opinion on that?
I think in that case, of course, you have to find out what does the kid understand, and where, you know, what are the things that interests him or her most. Because then, for instance, they understand maybe something else. Maybe it's something in sport. Maybe they understand music. Maybe indeed religion, or maybe there must be something that they do understand, and then, okay, you have to focus on that. I mean, you want the kid to function in society some way or other, and you want the kid to have pleasure from the kind of job it is doing. And so, yes, if they're not very well, if they're not willing or so to do something, it could be indeed a question of willpower, that their interest is something else. which is not in the curriculum of the school. So I think it's your job in that case to figure out what that is that the kid's interested in, and see if that gives you a way to develop its skill further, precisely in that thing it's interested in. Or maybe you have to explain to kids that that really isn't very interesting and it's not very wise for you to go into that field. If the kid's only interested in solving Sudoku puzzles or something like that, they say, well, you know, you can't make a profession out of that. It's silly. That's just. So you'll have to find something else that you're also interested in, and maybe something related, or. Yeah, if the kid really has nothing at all that is interesting, well, then we have a problem. Then we have a patient. Then it's indeed a problem for psychologists to figure out what's wrong with the kid. Why doesn't he use the function any possible way in society? I'm afraid I will not be able to answer that question. So then indeed you have a difficulty, but I think it's the scientists or the educators' problem to get something to somehow find a way to fill in the lives of such children, to make them lead a useful life in some way or other. Not every kid will be a scientist, I would never say that, because there are so many other things that you might want to do with your life. So find out what that is, and that way try to make this kid have an interesting life or a pleasant life, or feel at peace with whatever the future is going to be.
Good afternoon, Professor. My name is Yap. I'm from the Physics Department, University of Malaya. I do agree with you that kids are very smart and somehow they can manage very difficult tasks if given certain motivations. And to many young students, actually, physics and science are considered difficult subjects or difficult topics. And doing science or physics also does not relate to money making or lifestyle improvement sort of things. So if the students do choose to do physics or science and come to university, you have a lot of things to motivate them to go further. You have seminars, courses, discussion, summer college and regional school of physics or students, a lot more. But my question is, can you give some suggestions how to motivate young students or maybe kids to motivate them to do more, to do physics, to do science?
That is a very important, a very hard question. Maybe indeed one of those big questions of our society today. A big question actually, one of psychology, which is not really my specialty. So how do you really get kids interested in something that many are not interested in? And you agree with me about that kids do have the potential of doing a lot of science. They are very smart, but they want to use their skills instead to do chess or to do something else that also requires a lot of thinking, or perhaps do something other with computers, try to hack into the computer system or something like that, which also requires a lot of intelligence, but then this time they're motivated to try to do it. Well, of course, as a parent, I don't know whether you're a parent yourself also, but as a teacher, you also have to experience that kids often do not quite do what you say, but they do watch what you're doing. And so they sometimes find that, okay, my teacher wants me to do this, I'm not going to do this, I'm going to do that. And this is something that nobody else thought of. And I think actually there's an inborn sort of machinery in the human person that they don't want to do exactly as being told, that will bring you nowhere. If everybody would be doing what they are being told, this world would be very dull. No, we're going to do something else. And so as a teacher, you should have the flexibility to say, okay, if you want to do that, let me try to advise you here, because maybe, or let me try to get you to some other idea, because that's not a very good idea to go into this field, and explain to the kid why that's not an interesting thing to go into. For instance, music, there are so many musicians in this world, and there's so many very, very smart and excellent musicians. I think that sometimes there are more than we really need. And that's because people find it so interesting to make good music. And it is nice, I know, I like music myself. It's nice to try to excel in music. But, so some topics are more popular among people than others, whereas some topics are badly needed. Engineers are always badly needed. Today, computer scientists, well, they are badly needed. So if someone happens to be smart in computers, just give them all the room to try to enhance their abilities and skills in computer science, because we need computer scientists today. So there's nothing wrong with that. So as a teacher, you shouldn't try to push someone too much in a direction that they don't want to go into. That's not going to work. So you have to be flexible yourself, realize that maybe what the kid wants isn't so bad after all.
Yes, right at the back.
Idris from Malaysia. I think it is okay for small science and collective small science toward big science. But in collaboration, I do believe in a big way. For example, we have to choose one R&D project in Malaysia, or one R&D program, or one laboratory, and to have collaboration with one established program in Europe. And we have to do it in a big way. We have to plan, we have to organize, we have to implement in a big way with a lot of money, support from head of department, things like that, and we have to have a series of collaboration. If we undertake collaboration in a small way, send, for example, one scientist to Europe, and then another scientist coming, and then go to another department, send another scientist, and the other way around. I think that's quite difficult to achieve. One way, as I said, must be planned, must be organized, must be in a big way. We have to choose, for example, through Academic Science Malaysia, one big program, one big R&D project, for example, and we have to identify a partner from Europe, for example, and we can establish these two programs in a big way through a number of communication and through a number of years, a sustainable program. And through that, I think through collaboration can be effective, can be sustained, and can be successful. So what is your comment, Prof, on this?
Well, I understand the question is a question of choice. What kind of topic should we do, and who should be our partner in Europe or in the Western world in general, and which program should we follow? And this is a very hard question for me to answer, because it's obvious that it depends on the skills you have. I think you should look around carefully in your university and other universities where you find the most skilled people, and what the likely topics are in which you can contribute in a meaningful way. So I really believe that people can contribute most if they do exactly the things they are good at. So you find out the things that people here in Malaysia are good at, and say, okay, this is going to be the field where we are going to try to excel, be better at this field. We're already good at it, we try to be better at it. And that would be to collect more information on the subject, and to do it in an international way, so indeed send people to Europe, the United States, Japan, God knows where they can find more expertise on such subjects, and try to say, okay, this is going to be one of our specialties here in this country. But of course, I always advocate do as much science as possible, so try to be specialist in as many topics as possible, but yes, you have to make a choice. And then the choice should be, well, in what topics did we score best in the last years or so, and which topics, in which fields did we have excellent researchers. And that should be the choice, where you should say, okay, this field we are going to deepen and try to strengthen and try to show that this country exists and show to the rest of the world that there are good scientists here. And that should also motivate the people in question. Because they should be very motivated. The best way to have them motivated is to have them do more of the things that they already shown to be good at. That's also rewarding. You might want to win prizes or to get the attention of the rest of the world, or make a discovery that is being news in the media, then that's the reward that everybody will be after, and that will motivate people to continue along these lines. So of course I don't have a ready answer for these reviews, but I would say this is a strategy that you might want to follow to find the answer. We have in our country science agencies, or a government agency that distributes the funds for science, and they have a elaborate system of peer review. So you hand in a proposal, and they send the proposal to other people in the country, or sometimes people in other countries, to judge the quality of the proposal. And then they put all the proposals together again and they say, okay, this one scored better than that one, we are going to give funds to this particular proposal and not to that proposal. And so that's a peer review system that you need to select the best possible proposals. And then we say, okay, we go along with this one, it scored highest. Highest among the fellow researchers in this country, but also highest among the researchers in other countries that we managed to have, to ask them to have a look at this project and decide about what the best thing is.
Well, there's one person who was burning to ask a question. I saw his hand, I don't know how many times. Please.
Justin Abdulhalim from Academy Science Malaysia. I have two questions actually. First one is relates to the two previous questions which was asked by the two ladies. Focus on student. There is this stigma in the society actually that I'm very concerned of, in which that most of the time students who are not good in maths are always considered as not qualified or not good enough to go into science. So I would like to ask your opinion on this. Is it something normal, or is it something that we must do something to change that? Second question is that there has been a lot of new findings in science. For example, particularly on nanotechnology. And since you said that students are not really that stupid, so is it okay for us to introduce, for instance, nanotechnology at a very young age, or what do you think about it? That's my question. Thank you.
So it's a question about maths and a question about nanotechnology. It has always been a little bit difficult to motivate kids, students in general, to take math seriously, and that's understandable because often they don't really understand why should we learn all this, what's the use of these very crazy, these crazy symbols and rules and so on. And amazingly, as I remember from my own high school times, kids usually didn't ask these questions themselves. They just said, we find this boring, period. But they didn't say why. They didn't even ask why they have to know all this. That's because the teachers, because you want to have a grading exam. That was the reason why you want to know all this. That otherwise you fail for the exam. but they rarely ask themselves the question, why do I have to do this exam? What's the use of it? That's something that teachers should try to explain. We want to teach you this math because it's going to be part of any other technical subject you want to go into. For instance, our experience is that theoretical physicists from our institute, after they got their doctor's degree, often find a job in something like an insurance company or a financial company or any sort of firm where you wouldn't expect theoretical physics to be of any use. But it's not the theoretical physics that's going to be used there, but the mathematical skills that people have to develop. So the mathematical skill they develop by solving a physics problem turned out to be very useful in a financial company or insurance company or something like that, because there they sometimes need people who are mathematically not illiterate, so that they understand how to rephrase a difficult problem in its fundamental blocks and how to solve the combination of these problems in a logical, rigorous way. And for that, you definitely need mathematics. So kids can be motivated to learn mathematics by explaining to them why it is so important. If you want to become an engineer or anything technical, all math you can put your fingers on will be useful one day or another. So the more math you learn, the better you will be as an engineer or any other technical subject. But even in the financial business, math will be very useful. The other question of nanotechnology, well, it's a little bit of a hype that people have very high expectations of nanotechnology. Nobody knows to what extent that is justified, whether nanophysics or nanoscience will become as important as I always believe and many other people believe, but it's not totally obvious. Maybe it's hype and maybe it will go away as a very promising field of science. I don't think that. I think nanotechnology is going to play an important role in the future, but we don't know how and when. And again, I think kids who are interested, who are somehow, their imagination is being set off, they think, oh my God, this could be something very interesting, very important, I want to know more about it, then they should be taught about this, and they become future scientists who study nanotechnology in all its forms, to try to make it more useful, to find useful, applicable products where nanophysics is an important ingredient. I myself have very high expectations of nanotechnology, by the way, and I think that there will be big revolutionary technological consequences of that. But it may be a bit early now to have young kids. I mean, you must tell them about the existence of such a field, and that very smart people on this planet will go into nanophysics and they'll discover what you can do. There are enormous many things you can do, possibly in the subject, but others might want to specialize something different. So to subject all kids, that's too much. But they should know about it. They should know about all modern features of the society. They should know everything about computers, about also about the way the world works, about history, about cosmology. I mean, people want to know, and people are generally interested in these things. It's not true that these are only the happy few who are busy with a subject. No, many people want to know about what scientists find in the domain of cosmology, because it's just, it catches their imagination. We are part of the solar system is part of the galaxy is part of the big galaxy cluster in the universe. All these things are so tremendously interesting that, yes, it catches people's imagination, yes, they want to know about it. Same thing also in nanotechnology, it catches people's imagination, they know about it, but not everybody. And I think we should also need a little bit of a challenge. If something is there, you might want to jump on it, But don't, if you don't want to, then you will do something else. And maybe some people say, yes, now you say it that way, I'm going to look at that subject.
I would like to ask a question, actually. Sorry, I've got to close it now. There is about the problem of collaboration between Malaysian institutions and perhaps the institutions in the West. And perhaps even in your specific field, because as I see it, particle physics, etc., does require quite a lot of investment in capital and equipment. So how do you think it can work for Malaysia to deeper into the field of particle physics and so on?
Well, in mentioning collaboration among countries, I think you skipped the possibility of a collaboration of neighboring countries like Thailand, Vietnam, Korea, Japan, Australia. And in fact, I do know of collaborations of Southeast Asia, also in my field. So that's certainly something you should look at, simply because it's probably easier to travel to Korea or to Vietnam or China perhaps, because they're closer by. And I think it's an important thing you should look at. Of course, you also look at Europe, you also look at the United States. And again, think of projects that you want to participate. I think Malaysia is also the list is very well of those states who are observing states of CERN, for instance. And so people do come to CERN in Geneva to study what's going on there and to be part of the show. And I think that's a good thing, that people should be at least aware of the big labs and take a small part of it. But the same for other countries. But there's enormous potential in this area of the world. And to have collaborations here, probably if you think of building a big particle facility somewhere in this area. Of course, Japan has accelerators machines, but Malaysia itself is too small a country to have the huge big laboratory in its territory. But in collaboration with other nations, I don't know what the total number of inhabitants is in this area if you count all the neighboring countries. But then you got if a new upcoming economy, I mean, economists all seem to agree that this is an area with new potential in all respects, so maybe also in science, and big projects on this.
Ladies and gentlemen, I know that it should be time for us to stop. But before I do, I'd just like to find out whether Mr. Uwe Morowitz would have to have a few words to say, so he choose not to. I would like to just summarize, as I was very fortunate to have ghostwriters to map out the points that was covered this afternoon. But before I do that, there were 4 items that I'd like to just touch on. First was a question on language that was raised, and I think you answered it very well on why English should be used. And because it is still a very controversial subject in Malaysia, whether mathematics and science should be taught in English. But I would like to claim the credit, or you can blame me for putting the language question in, because I was a member of MACBEN, which is the economic foresight that was set up a government, and I was chairman of the science and technology back in the year 2000. I must admit that I didn't expect the implementation to be so sudden, but the idea was simply, we are saying that if you are going into the future, we have to make the sacrifices, and the earlier we do it, the less painful it will get. Yes, we will have problems of startup. Yes, we will have problems of rural children having difficulty and so on. However, we feel that with modern IT and television and so on, as children are not stupid, they can pick up English pretty fast. Second, the question of brain gain, which I think was alluded to but not mentioned. We have a program where to encourage universities here to have linkages with overseas, and people, the experts, whether they are people in the laboratory or they are the professionals or people who are distinguished professors and so on, to come to Malaysia for a period of perhaps 2 years, on and off, and collaborate with Malaysian universities to do research and develop teams here for this purpose. So, Academy of Science is given the responsibility to do that, and a certain amount of allocation is given by government. And I'm chairman of that committee in the Academy of Science, and we are not yet satisfied with the number of applications that we get. So we would like for you to, particularly those in the universities and the research institutions, to make use of this collaboration and to use the funds as available. I think the other point that I thought was of importance also to mention was the fact that the professor was losing his voice, and I thought it was unfair for us to continue. But nevertheless, I was fascinated by what he has covered. Unfortunately, perhaps you didn't know that some of the people who are here this afternoon was not here in the morning. This is a fresh, few of them have been to both sessions, but a number of whom only came here in the afternoon. So there are times when we have to explain twice, and we know why, because they were not here earlier. But ladies and gentlemen, I'd just like to cover the things, the notes that has been made by my repertoires. And these are the things that we've discussed this afternoon. First, we are really asked about how do we create a Nobel laureate. There's no shortcut, and I think the Professor mentioned that it's a chance event, and it's luck, as I said, but also there is a need for us to increase the number of scientists per start, and the depth of which scientists should do in order to increase the probability of finding somebody who can be a Nobel laureate. And I think you also mentioned that maybe we should look at what we are good at. So MPOB is around here with palm oil. They're doing research in palm oil. Not many other countries do that. Maybe that is one area that the potential Nobel laureate can come from. We don't know. But again, it's a chance that we can do that. The other thing that you mentioned also is train them young. And I think you covered that well. And the teachers who are interested in that area raise questions and say, how do you teach a reluctant student, or a student who do not want to do mathematics? And I think you gave a very good answer. Well, those are good for football, let them play football. And otherwise, but not everybody wants to do mathematics and science anyway. And I think it's a reality that we look at. I think you also gave us this very good point of saying, be critical, self-critical if need be. And I think some of us are a bit too sensitive about being criticized. But I think what you're saying is challenge and be challenged. Issue number 2 was we're talking about, again, I have to mention about this English earlier on, and you've helped stress the importance of English for both advancement in science and also to create a collaboration for the future network at international level. Issue number 3 that was raised was creating science as a culture. That is to create a clear distinction between respectful and as well as being critical. I think you did mention that several times, and I thought that we sometimes forget that. Also to understand science as a collective body of knowledge. And it is not just done by one person, although I think you said in your own case, you did quite a lot of work yourself. But it does require collaboration with others, and it has a need also even to form societies or groups, whereby to challenge those ideas and to critique yourself, and to open yourself to criticisms. The other issues that were raised also, that we were looking at organizations to create role models and to ensure that science is actually popularized. So perhaps we also need to find the right balance between being critical and being respectful. I think you mentioned this quite well when you were listening. You also dared to go through fairly sensitive questions like religion and science. and how to marry the two. And as you notice, perhaps people in the East, we are more spiritual, we are more accommodating. We do not think that science is exclusive. We think that it's inclusive, and that we can be both religious and scientific at the same time. But it's inspiration, you said, is essential, and the source of it, although, is a personal matter. So we take note of what you said. And the last item that I've got here is actually teaching of science. You've raised it again and again, that there is a need to be systematic about it. There is a need to have exercises, and also to treat complex problems, but break it down into simple problems which are more manageable. And you also address those ideas that was asked, whether if one is not good in maths, what do we do about it? And again, even areas like exotic things like nanotechnology, when and how we can look at that kind of questions. Ladies and gentlemen, I believe we really had a wonderful afternoon, and I think all of us have learned something. And so I would particularly like to thank the founding chairman of the International Peace Foundation here for making this whole thing possible. I would also like to thank the Open University for enduring us and putting us in this very nice hall. Although earlier on we had some distractions from the tables, but I think we should forget about that very soon. And I think for all of you who have taken the trouble to be here this afternoon. But finally, the person whom we were so fortunate to hear from today, Professor Gerardus at Hooft, I'd like to invite you to thank him in the usual way. Thank you.
Thank you. Thank you, Professor Hooft, for an interesting and insightful dialogue, and Dr. Zaidi for moderating the dialogue. With that, ladies and gentlemen, sorry about that. With that, ladies and gentlemen, we've come to the end of this dialogue and hope you have benefited much from the discussion and the sharing of ideas. We look forward to your participation in forthcoming Bridges events, which are detailed in the program books that were distributed to you earlier. Everyone is cordially invited for refreshments that will be served just outside this room. So thank you once again.